عليكم ورحمة الله وبركاته. في هذه الأمسية الجميلة محدثكم ياسين مليكي من قسم علوم الفلك والفضاء بجامعة الملك عبد العزيز. أرحب بضيفنا وهو صديق عزيز بروفيسور ديفيد ألكساندر، كما أرحب بالحضور الكريم من السيدات والسادة المهتمين بهذا العلم من جميع الجامعات والجمعيات والمراكز والمعاهد من هواة ومحترفين. في هذه الليلة سيأخذنا ديفيد في رحلة استكشافية عن الكواكب الخارجية والإكسوبلانيتس، وكيف يتم استخدام معرفتنا عن التفاعل بين الشمس والأرض لاستكشاف تأثير النشاط النجمي على هذه الكواكب. وهذا نوعا ما يعني تخصص علمي جديد في هذا المجال، أنه تربط بين الانتراكشن في السولار فيزيكس مع الأرض والعلاقة وما نستطيع أن نتعلمه من خلال الإكسوبلانيتس وتأثيرها أو تأثير النشاط النجمي عليها. اللقاء بحول الله سيكون المحاضرة ديفيد حيلقي Goldilocks Planets and the Search for Habitable Worlds. بعدين إذا في إمكانيات، هو الحقيقة عنده موعد الساعة 9:15 فمضطر إنه يمشي، وهو مرحب يعني رحب بأنه يكون في علاقات بين جامعة رايس يونيفرسيتي، وهو رئيس قسم الفضاء هنالك. أنا حتكلم عنه الآن، والتعاون معنا في قسمنا بحول الله تعالى حنتحدث عنها في الأسابيع القادمة إن شاء الله. هذه السلسلة المحاضرة من المحاضرات هي آخر سلسلة في هذا الفصل يقدمها قسم علوم الفلك والفضاء، وكما تعلمون أنها تهدف إلى استضافة علماء مميزين في مجال علوم الفلك والفضاء. استضفنا العديد منهم في الأسابيع الماضية وكانت حلقات متميزة، واليوم نستفيد دكتور ديفيد ألكساندر، وهو يعمل في مجال الفضاء والفلك وله علاقات قوية بناسا وبحوث مشتركة مع ناسا. ومن الأهداف أيضا هي مشاركة ومناقشة آخر ما توصل إليه العلم في مجال الفلك والفضاء، وخدمة المجتمع التعريف بهذه العلوم. يعني القسم عندنا نشط حقيقة جدا في موضوع علوم الفلك والفضاء والريسيرش والأبحاث، وخطى خطوات كبيرة جدا. I'm going to speak in English now, please, if you allow me, David. So David is my great friend. We know each other since 1987, I think, David. In astronomy,
yeah, that could be right.
Yes, in mathematics building, Glasgow University, and he helped me a lot in my typing mistakes, and I am very grateful, as well as some badminton and squash, although we did a little bit of that techniques with Yan Chao, if you remember him, our Chinese friend, and Alan David Cromwell, the rest of the group. I was very happy to study there with a nice group, actually. David is always helpful. He came to Riyadh, Kakist. Was it in 2005, David? Or...
Was it that long ago? I don't remember. I think, yeah, it may have been. I can't remember. It was a while back.
It is. He came and he did gave us fantastic lectures about solar activities, and I think was it about SOHO or interaction.
Well, we were talking about telescopes and looking to put potentially a telescope in Saudi Arabia. So that's why I was working with Prince Sultan and a few of the others. Yeah.
Exactly. And now you've heard that 2 years ago, I think in December 2018, Saudi Space Commission has been established, and Prince Sultan is very active, and the group with him, they are very active in constructing a very good space commission. Let me talk a little bit about our pioneer, Professor David Alexander. David is a professor in the Department of Physics Astronomy, where his primary area of research was solar physics, exoplanetary physics now, and Earth remote sensing. He serves as the director of Rice Space Institute, where he is responsible for providing vision, directions, and leadership, managing the various institute program, identifying and fostering research opportunities for the faculty, Rice faculty, and interacting with government and the space industry. And he is very active in this area. I'd like to congratulate him so much, although it's a bit late, for he was awarded OBE in June 2018 for services to the space industry at home, and he got the medal from Prince Charles, I think. Is it, David?
Yeah.
Yes. He received also presented Early Career Award for Scientists and Engineering in 2004 and was appointed in Cavalier Frontiers Fellow by the National Academy of Sciences in 2006. He is former chair of Solar Physics Division. I know he doesn't like to talk too much about solar physics now, but and of American Astronomical Society.
I always like to talk about solar physics.
Is that? Okay. He has served so many professional committees. That's great, including NASA Advisory Councils, Heliophysics Subcommittee, the NASA Solar Heliospheric Management and Operations Working Group, NASA and ESA Solar Orbiter Payload Committee. That's great. This year they sent.
Yeah, they launched successfully, and yeah, they're on their way.
He also currently serves on the advisory board of SpaceCom, the Sasakawa International Center for Space Architecture, and on the additional board of Space Science Reviews and Room. You've been very busy, David.
Yeah, too much to read out, so you don't need to read it.
The final paragraph. I love it because, you know, it gives the people, the audience, the great background you had. Space Journal, he has been named a Global Scot by the Scottish government and was elected to the board directors of the American Astronomical Society in 2018. Finally, he joined the faculty at Rice in 2003, that's 17 years ago. He received, of course, his Bachelor of Science in Natural Philosophy and Astronomy and his doctorate with in my department, relative cosmological models for the University of Glasgow. David, honestly, we are very, very delighted and happy to have you this evening. And kindly, you have, I know your schedule is tight, so 45 minutes is okay?
I'll try. Talk too much.
But very, very fruitful. Thank you. Kindly, you can start, please. Thank you. And by the way, there is a translation Arabic. David عامل translation ليكم باللغة العربية، فإذا في أخطاء تعذروه واللوم تحطوه على جوجل. Please, David.
Shukran, Yasin. Hopefully, the translation will be accurate. I can't promise, but it's just automatic system. I do have very fond memories of Yasin in Glasgow with his family, very young family at the time. I thought he was very lucky, and that was more than he deserved. But we had a good time in Glasgow, and it's great to see him. I've only seen him maybe twice in the last 20 years or so, but it's always great to see him. He's always a joy to be with, a lot of fun. So what I'm going to try and do today is it's a broad audience with some members of the public, as well as some students and some faculty in astronomy. So I'm going to try and give you a rough overview of the issue and some of the things that we're doing. And the key thing that we're focusing on here is how we take all of the knowledge that we have in understanding the sun and the sun's interaction with the earth, and to apply this to these new systems. And so I'll give you a little bit of introduction to the new systems as we go. You may not be familiar with the phrase Goldilocks. It's a story that we have in the West that is this little girl who comes upon a house that's a bear's house. And I won't tell you the whole story, but basically she tastes the breakfast porridge, the oatmeal, and one is too hot, one is too cold, and the other one is just right. And so when we look for habitable planets, traditionally planets that may support life, we want it to be not too hot and not too cold, but we want it to be just right. And so we refer to them as Goldilocks planets. And I will show you hopefully tonight that it's a little bit more complicated than that. Of course, I've got many collaborators, and they're listed here from Rice University, and a friend from my old stomping grounds of Lockheed Martin. Now let me see if, okay. So one of the things about the sun is this is a quote from an old friend of ours from Stanford. Basically, the sun is the only star we know of that grows vegetables. And that's a kind of fun way of saying that the sun is the only star we know of that supports life. And so that up until maybe 20 years ago, it was the only star we knew for sure had planets. And so with the first discovery, there was a discovery in 1991, but the first discovery of a regular planet around a regular star was 1995, so 25 years ago. And those discoverers were just recently awarded the Nobel Prize. But if you're an astronomer, the sun is quite boring. I don't know if you can quite see this. The sun is in here. There's a whole range of really interesting stars. This is called the main sequence. And I really don't have a lot of time to give you all of the background in astronomy, so hopefully some of you know this. But the sun is essentially, when it comes to interesting stars, the sun isn't that interesting, except for the simple fact that it has life. And so we can learn a lot from that information, the fact that it supports life on a planet like the Earth. And we can then start to think about how we might look for signs of life on these other planets. Now, before we go to the other planets, we're not done looking for life elsewhere in the solar system. Obviously, we have life on the Earth. We're still looking for life on Mars. And we have a rover, two rovers, one from the US, one from Europe, going out to Mars right now. And they're going to be looking for potentially microbial, or at least evidence of microbial life on Mars. At the very least, we would like to know if life existed on Mars in the past, when Mars was a little bit more like the Earth, with a strong atmosphere and we think liquid water on its surface. And so we haven't given up finding signs of current or at least past life on Mars. We're also interested in the moons of Jupiter and Saturn, the icy moons, which we now know have large quantities of liquid water, even though they're so far away from the sun. This is Europa, which orbits Jupiter. And that is 5 times the distance from the sun as the Earth. So quite far away. Average temperatures are very cold, but because of it has a very thick ice layer, and we think because of those pressures, there is liquid water underneath the ice, which could be 40 to maybe 100 kilometers thick. And then on Enceladus, this is a moon of Saturn. It's 9 times further away from the sun than the Earth. But these little things down here are called tiger stripes, these little blue lines. And from those tiger stripes, they're slightly warmer than the background. And there are ejecta, there's plumes of vapor that come out of those, and that those plumes actually have water in them. So again, evidence that there might be liquid water on Enceladus. And if you follow the news, you will know recently that there was an interesting discovery in Venus with a compound called phosphine found in the upper layers, or still to be confirmed, but tantalizing evidence of phosphine in the upper layers of Venus's atmosphere. And one way to produce phosphine is via organisms, microorganisms. And so there's some now excitement that there, even though Venus is a crazy planet, it's 450 degrees centigrade night and day everywhere around the planet, and rains sulfuric acid, a whole range of stuff that you would not think as being hospitable to organisms, but there is some now tantalizing evidence that they exist there. So we're really excited about potential evidence of life elsewhere in the solar system. It won't be like us, it will be more like microorganisms at best, but that's some excitement. Now, if we go further afield, one of the things, again, if you follow the science, to date, we have confirmed the existence of 4,306 planets around other stars other than the sun. And you can see the breakup here. Most of them are very large planets like Neptune or Saturn or Jupiter. A vast bulk of them are like that. There's a few, a good percentage of them are very, very large Earth-like planets, but very, very large, like maybe 10 times the size of the Earth. And then there's 100 or so that are a bit more like the Earth or Mars or Venus. And of those planets, some small subset of them are in what we call the habitable zone, and I'll talk about that in a second. These 4,000 planets are distributed in 3,000 different systems. So in other words, there are 3,000 stars and 4,000 planets. That kind of just indicates, because it's very difficult to see these things, that just indicates that probably most of these systems are multi-planetary systems, just like our own solar system. And the other thing I would point out is that this 4,000 planets have been detected from a relatively small piece of the sky for the most part. And so if you do some averaging, if you think about the statistics, this could imply that there are as many as 100 or 200 billion planets in the galaxy alone. In other words, roughly one planet per star. So this small number. It's a large number compared to where we were. 4,000 is a big number when compared to one. But we think this implies that we will find planets pretty much wherever we look. The question is, what do those planets look like? Can they support, are they like the Earth? Are they like Mars? Are they like Saturn? And so one of the things that we have been exploring is, as we've now got lots of planets to study, what's the physics of these planets? How do they interact with their parent star? And so that's the key focus of what we'll do today. I just wanted to give a basic background of how we detect exoplanets. I'll try not to take too long on this. The two main ones I'll focus on are the first two. And that is radial velocity measurements and transits. In the little video you saw from the department before Yassine came on, you actually saw a movie of a transit of the sun. I think it was Venus. It looked too big to be Mercury, but we see transits of Mercury across the face of the sun and Venus across the face of the sun, and those allow us to, when we look at distant stars, to find these planets. The other aspect is that planets have a gravitational effect on the star, and we can look for that gravitational effect. So the vast majority of the planets come from that approach. There are some planets that have been directly imaged. That's challenging because of how bright the star is. And then there's an interesting piece of physics called microlensing that we can save for another day. And then there are some other observations from other techniques that aren't included in these statistics. So this is a plot of the very first planet observed around a star. I've put the math in for Professor Amliki's students, but I won't talk to the math tonight. And the basic idea is that two objects, a star and a planet, the planet doesn't, well, the planet orbits the star. Well, all right, back off a second. Neither of those objects orbit each other. They orbit the common center of mass. And so that center of mass is where the gravitational balance between the two bodies lies. Now, of course, for a planet and a star, that center of mass is inside the star. It's a fictitious point in space. And so when you have a planet with its own gravitational effect orbiting the star does a wobble. And the star moves around in its own orbit about the center of mass. And when the star moves towards us, it does something interesting to the light. It's a thing called the Doppler effect. And so the light changes its color. And when it's moving away, it changes its color in the opposite direction. So you would imagine a yellow light turning to be close to red when it's moving away from us, and becoming more blue when it comes towards us. And so I'll show you this movie, and you'll get a sense of that. And because of that, we can monitor the wobble of the star. And that wobble is caused by gravity, and that gravity is caused by a mass. And we can work out that and because it repeats, we know it's a planet for the most part, and that we can measure that planet's mass. So if you watch this little video, you'll see what I mean. So there's the star orbiting its center of mass because of the planet. The light is now turning normal, yellowish. Now it's coming towards us, so it's blue and bunched up. It comes back to yellow, goes and then moves away from us and starts to become wider, a larger wavelength, and redder. And so by watching this repeat pattern, we can map that out. And then just basically because of Newton's law of gravity and a few other little clever mathematical things, we can use this information to learn something about the planet and its orbit. The orbit is how often this repeats. And this is not in days, but this turns out, if you look at the analysis of this planet, it was a 4-day orbit. Now the Earth goes around the sun in 1 year, 365 days. So this is very close in. Mercury, which is the closest planet in our solar system to the sun, it has an orbit of 88 days. And so this planet is significantly close into its star. And then if you look at the mass, apart from a couple of little observational things, its mass is about the size of Jupiter. So if you think about this, it's a Jupiter-sized planet orbiting very, very close to its star. That doesn't look like our solar system at all, and that's a whole other discussion there. But what it means, what the whole point of this is that in order to see this effect, our telescopes are not so good that we can see everything. In order to see this effect, the planet has to have a large mass, so it has to be really big, and it has to be very close in, so it cannot look like our solar system. It's very difficult to detect an Earth-sized planet going around a sun-like star at the distance of the Earth from the sun, for many different reasons. So this is the technique, and from that we can actually measure the mass of the planet. Now, the other technique, The other technique is when, and this is a little bit easier to understand, is that from your point of view, when the planet passes in front of the star, it blocks some of the light. And so for the time of the transit, for the time of that passage, the light of the star is lower than it was when the planet was not in the way. And then because the planet is orbiting the star, this pattern repeats. And so if you watch this video, this is just focused on the transiting part. So you're looking now, and here comes the planet. This is the light from the star. Boom, it drops, picks back up, and then the planet goes around in orbit, and it repeats and repeats. So from the repeat, you can understand that it's an orbiting object, and from how much light it blocks, you can tell how big the planet is. Now, we can't measure its mass from this technique, but we can measure its radius, its size. And so again, this is where most of the planets have been discovered by this technique, roughly 3,000 out of the 4,000. And I was going to say, yeah, again, this is biased towards large planets, now large radius planets close in, because the large planets close in block out more light and therefore they're easier to detect. So all of our systems right now are biased towards large planets close into the star. So those are two of the techniques that let me pause this and hopefully move on. These are some of the techniques that gets us to this number of 4,000 planets. And again, if you want to see all the statistics, here is the website here. Okay. So the habitable zone side of things, one of the things, and again, there's some interesting physics in here. Here's the Earth, and here's the Sun. The Sun is what's called a cool star. Its surface temperature is about 5,800 degrees Kelvin, so close to 6,000 degrees. We have hotter stars that can go up to 7,000 or 8,000 degrees. And we have a lot of cool stars down at 3,000 degrees. These are called M dwarfs, and the Sun is a G star. There's K stars and F stars as well. So it's just a little label that astronomers give. And the way you do this is you say, okay, how bright and how hot is the star? How big and how far away is the planet? And you look at how much energy the star can give the planet, how much the planet can radiate, and you look at that balance, and that allows you to work out the temperature. And if the temperature lies between 0 and 100 degrees centigrade, you can have liquid water. And so that defines what we call a habitable zone. Its temperature is just right. That's the Goldilocks zone. It's not too hot, it's not too cold, it's just right. And so the Earth, this green region, maps out the extent of the habitable zone for these types of stars. And so you can see here's the Earth. Venus is just about here. It's just right on the edge, a little bit too hot on the edge. And Mars is just about out here at 1.5. So if you were to look at the solar system from a distant planet, if you were on one of these exoplanets looking back at the solar system, you'd be very excited because you would find that there were 3 planets orbiting the Sun that were inside the habitable zone: Venus, Earth, and Mars. Venus and Earth are roughly the same size, and Mars is about half the size. So those are 3 pretty good planets orbiting a reasonably active star, not too active, at the right distance. And so you would be so excited, and this is where I'm making a dig at my friend Yassine, because this is what got people excited about TRAPPIST, and he's worked on some of the TRAPPIST systems. I'll mention that in a second. But if you were to look at the system, the solar system from a distance, you would see that there are 3 potentially habitable planets. But look at what we know about those 3 planets. We know that Venus is crazy, right? Venus has a huge runaway greenhouse effect, so that its temperature is ridiculously hot, 450 degrees centigrade. We go to Mars, and we know Mars hardly has any atmosphere because it was so small that it lost its magnetic field 3 billion years ago. And because of that, its atmosphere was stripped away by the solar wind. So while we're still looking for potential microorganisms on these planets, we know that they don't support complicated life to the present day. And so you have to be careful when you use this temperature zone as the key thing. Now, the other thing I want to point out is that if you remember, one way to detect the 2 main ways to detect planets is if they're big and if they're close in. So if you imagine taking an Earth-like planet, in order to detect its gravitational effect on the star, either by the crossing the front of the star and transiting, or via the radial velocity, via the gravitational perturbation to the star, that planet has to be really, really close in. So because Earth isn't such a large planet. So if you want Earth to disturb the star, and if you want an Earth-like planet to disturb the star so you can see it, and you want it to be in the habitable zone, you have to go way down here. You have to look at really cool stars, because you can only detect planets that are close. And if you want to be in the habitable zone, you can't be up here. So you have to be looking around cool M-dwarf stars. And it turns out those M-dwarf stars, very many of them, are very much more active in the sun. And that's what we'll be talking about going forward. So here are some of the celebrities. Proxima Centauri, all of these stars are these little red dwarf stars. So they're called M stars, if I go back. So these are M stars. They're about 3,000 degrees. They're much smaller. Proxima Centauri is about 1/7 the size of the sun, for example. So these are small, cool stars. And so all of these stars are in that category. Proxima Centauri is a celebrity because, of course, it's the closest star to us. It's only 4 light years away. And it has a planet, if you ignore this little factor here, it has a planet that's roughly the size of the Earth. But that planet is orbiting in at 1 astronomical unit is the distance. So if this number is 1, that's the distance between the Earth and the sun. So this orbits 20 times closer to the star than the Earth does to the sun. So that's a very close in orbit. And Proxima Centauri is a very, very active star. You can have as many as 50 stellar flares in a day, whereas the sun might have a big flare maybe during maximum once every day. So this is a very, very active star, and we'll show you what that means in a second. TRAPPIST is interesting. This is the TRAPPIST system up here. TRAPPIST is the name of the star. It has something like 7 Earth-like planets. 3 or 4 of them are in the green zone. And so that's a very interesting, and again, Professor Amliki's done some work on TRAPPIST. The problem here is, the problem here is, this is where Mercury, I don't know if you saw this pop up. On this scale, you can't maybe see these numbers, but on this scale, Mercury is way over here. So all of these planets orbit well within the orbit of Mercury when you consider it, when you consider the solar system. So all of these planets are very close in as well. And TRAPPIST is quite an active star. These two, Ross 128 and Teegarden, are getting a bit of interest because they're further away, 11 light years and 12.5 light years. But they're not very active. Ross is the one that's very slowly rotating, so it's not very active when it comes to flares. And Teegarden is also showing very little activity. So these, and they have planets around them, roughly about the size of the Earth. And these are cool stars, so this distance isn't such a problem. And so they're less active. So these are kind of interesting stars to maybe go look at, as opposed to Teegarden. But even there, we'll show you that there's a problem. So I'm not going to read all of this to you, but essentially we know by studying the sun that there are many ways in which the sun interacts with the Earth. High energy electromagnetic radiation, X-rays, and extreme ultraviolet radiation. There's a solar wind, and most stars, most magnetized stars, we expect to have a wind. There's magnetic fields that interact with the Earth's magnetic field. You have large solar flares and coronal mass ejections, and I'll show you some movies of those. And you have long-term variability in the cycle, which can have long-term effects on the conditions on the planet. So we're going to take that knowledge and apply it to these new systems. So before I do, I'm about to show you solar activity. These are real observations from our own sun, taken from some instruments that we put in space. And you will see what I mean by activity in 30 seconds. There'll be no quiz, but you'll see what I mean. Hopefully you'll hear the music too. Oh, maybe not.
No, there's
Anyway,
no sound.
yeah, I can't hear it either, so I must have switched it off. So what you're looking at here is essentially a whole range of different kinds of solar activity. I'll hone in on a couple in a second, just so that we can talk about them. But these, I want to point out, these are real observations. This isn't a CGI Hollywood movie. These are real observations. And the sun is not regarded as a very active star. So that just lets you know what some of these other objects can look like. So if we think about solar flares, you'll see this movie. Notice there's nothing up here until this happens. And in a second, you'll see the size of the Earth show up. So all of that is energy being released by the atmosphere of the sun, from the magnetic fields in the atmosphere of the sun. And there's the Earth. So if you think of the Earth, now the Earth is very far away, of course, but this volume, this amount of that star is enormous. And so the amount of energy that the stars release is very large. And then here's my favorite. So we're looking at a singly ionized helium. So we're looking at plasma gas that's about 80,000 degrees. If you look at this little thing here, that looks like someone scratched the lens. This is known as an active region filament. It's actually about 50,000 kilometers across and about 5,000 kilometers above the surface. So here's this thing is a star. This is the sun. You can fit 1 million planet Earths inside this star. Watch this tiny little thing. Boom. So this is known as a filament eruption. And that tiny little thing just went nuts. And it released all of this. I'm sorry?
It's very huge and immersive.
Yeah, so we have to try and understand how that little thing could store enough energy over time and then suddenly explode, essentially, for want of a better word. And then we can start looking further away. And we do all this. These are all solar observations. So we're doing this with the sun. You can then look at what happens as you go further away. So what we've done here is combined data from 3 different telescopes. Here's the sun. We've colored it green because we can. This is now looking at gas that's 1.5 million degrees Kelvin. Then this black disk is a second telescope where the sun has been blocked by a disk, like an eclipse, and we can see the faint stuff around. And then the third telescope has a bigger disk, so it's blocking not just the sun, but this inner region. And then it goes out to about 20 million kilometers out here. So the Earth is still a long way away, but you're going to see one of these, you can't see it on this scale, but one of those little filaments is down here and it's going to erupt. Now, again, this whole thing is a star, right? So this is 1 million planets of the size of the Earth can fit inside this circle or this sphere. Watch what happens when we get a coronal mass ejection. Boom. So that tiny little thing turned into this, which is much, so if you look compared to the size of the star, this is huge. It's moving at about 1.5 million kilometers per hour. And as you're looking at it, you're the Earth. So this one didn't bother the Earth. When it comes towards you, so the sun rotates, so 7 days from now, if that same thing happened, when it comes towards you, this is what happens. So again, here's the sun, we've made it red now. Here's our big disk. So we've blocked out the sun and the inner circle that we had before. You can see this, you can see the stars in the background. You can see the solar wind stretching out the magnetic field. And then here's what happens when one of these events occur coming right at you. Boom. And then you get this. So what's happening is that coronal mass ejection is, we're missing the center part because remember we're blocking it. We've got a disk in the way. What it's doing, it's a bit like a speedboat on a river. So the solar wind that you're seeing here is the river, and then out comes a coronal mass ejection like a speedboat. and it creates a shock, like the bow shock. If you see the around a speedboat or a jet ski, you can see that wake in front, or the wake behind you, and the shock in front of you. Those shocks can take these protons, these particles in the solar wind, and accelerate them up to close to the speed of light. And then those particles start to interact. Here they're interacting with our camera, but they also can pass through spacesuits and damage, do genetic damage to astronauts. They can short circuit spacecraft, a whole range of activity we call space weather. But again, this is the environment in which all these exoplanets live. They live in the atmosphere of the star, and many of them are much closer than we are here. And so that's something that we're hoping to explore. And I'm going to have to watch my time. I get too excited sometimes and I talk too much.
It's okay.
So hopefully you're getting a sense of at least what we know about the sun, and then how we can start to apply that.
It's amazing, David. Love it.
Well, this is the data that we've been. I mean, I used to when I worked at Lockheed, we built a bunch of these instruments that took this data. So let me not go read all of this, but again, what we are doing is we're trying to understand what happens back at the star and what happens at the planet. And ideally, we also want to fill in the gap with the wind. We're not there yet. We're working. I have one student working on the stellar part, and I have another student working on the planetary response part. And so let me just give you basically. So this is a flow chart of what we're doing. We have a model for how the sunspots appear on the sun, and then how they move around the sun. We can then take those sunspots, we can take our model of the sun and change its parameters so that it can look like a more active star or a less active star. What this is just trying to show you is that when there's lots of sunspots, lots of magnetic field, your atmosphere gets very hot. So each one of these blue suns, this is data again. This is solar maximum, solar minimum, very few sunspots, back to solar maximum. Each one of these blue stars has a corresponding red star. This is X-ray emission from the star. So this is gas that's been heated to 3 or 4 million degrees because of the energy released from the magnetic field. And again, that takes a long time to describe, and I'll skip over that. So we're modeling the emergence of this magnetic field, this source of energy. We can also model the electromagnetic radiation that comes out of that magnetic field, and we can add in some solar flares. When we get to the planet, we have to look at how the planet responds to the input of energy from the wind, from the magnetic fields, and from the enhanced electromagnetic radiation. And we put all those together, and I'll show you that model in a little bit. So to cut to the chase, without going into the details of the model, in the center is a simulation of the sun. And I know it doesn't look much to you, but this actually is pretty good. When you look at the sun, this is when there's lots of sunspots, but they're all scaled to be the same level. So you can see lots of spots. This is what happens when you crank up the activity by about a factor of 30. So this is a much more active star. This is a much less active star. I think I updated this image to have a better representation, so I apologize, I forgot to update this particular slide. But essentially what we can do is we can take the sun as a reference. We can increase the number of sunspots, or we can decrease them. We can then work out what this is called like a Nerf Kush ball, we call it in the United States. You can work out what the magnetic field is in the atmosphere of the sun and where it can interact. The green and the magenta lines, that's where the solar wind can escape. So we can look at how much solar wind there is. You can see that this has got a lot more structure, whereas this is relatively simple. This is called a dipole. It's like a bar magnet, North Pole, South Pole, and then your little field lines here. So the point here is just that we can model this and we can let it evolve in time. And when we do that, there's a weird thing called the Alfvén surface. The best way to explain this is through a bunch of equations, but let me just simplify it a little bit more. At some point, when the wind is leaving, the solar wind is leaving the sun, its velocity, its speed is increasing. And there's a point at which it increases, it gets to a value that's bigger than what we call the Alfvén speed. And the best way to think about this is that the wind becomes supersonic. Technically, it becomes super Alfvénic, but just for picturing your head, the wind becomes supersonic. And what that means is that the wind is now completely separate from the star, because anything that happens on the star is moving at the sound speed, or in our case, the Alfvén speed, and cannot catch up with the wind. So the wind is decoupled from the star outside of this surface. Now, why is that important? Because if you're outside this surface, like the Earth, the wind isn't connected back to the star. So the Earth is like a rock in the river. It's an obstacle in which this flow, the wind passes over, and you get certain amount of interaction. If you're inside the Alfvén surface, the planet is then connected right back to the star magnetically. I think if I do this is some model, just again, we won't do detail, but if you actually model the magnetic field of the planet, the star is somewhere up to the top right. If you're inside this surface, instead of having a nice bubble of magnetic field like we have on the Earth, the magnetic field is connected right back to the star. This is a bit like sticking your hand on the top of your stove while it's on. You're connected directly to the source of energy. You're not separated from it. That is not good. You will lose your atmosphere. You will not have stable conditions on the planet for life to generate and evolve. And so it's not good to be inside the Alfvén surface. Now, what we have done, and again, I don't know, we've taken our model. We along the bottom, we're going from right to left. We've got increasing activity, more sunspots. The sun is at 1, is here. And what we can do is we can work out where is that Alfvén surface. So again, I don't have time or to go into all the details, but we can look if we're at stellar minimum, the surface is up here for the sun, and it's here. When there's lots of sunspots, it's here, a little bit closer in. And so as you go and as you crank up the dial, as you make the star more active, when we go from 1 towards 0.1 here, then that Alfvén surface, that surface moves in, and it gets complicated because it gets kind of combined in here. So the bottom line, though, is this is where we think this pink area and this blue area are where we think the Alfvén surface is as you increase the activity of the star. So that's nice. That's a good scientific result. Distance from the star is up, increasing activity is right to left. The thing I want to point out is look at all of our celebrity planets. Here's Dr. Amliki's favorite TRAPPIST system. Very close in, very active star. So the star is way down here. All of these planets are inside that star's Alfvén surface. So even though they're in the habitable zone because of temperature, they are not conducive, in my opinion, to habitability, because they are we believe that they're magnetically connected to the star. So again, not good. Here's Proxima Centauri, less active than TRAPPIST, but more active than the sun, also inside the Alfvén surface. Here's this low activity star, Ross 128, again, inside its Alfvén surface. And then here's the other one, Teegarten. Now this one, GJ, is interesting. This planet is inside its Alfvén surface. This one is just outside. So that would be kind of interesting. The problem is, this is the planet that's in its habitable zone. This one is outside. So this one might be good magnetically, but it's not good from a temperature perspective. This is not in the Goldilocks zone. So this is the kind of analysis we can do. We've picked a few stars here. We've tried not to be very specific about which one. We don't model the system. What we do is model the magnetic environment, and then we can see where these systems lie within that environment. So there's lots of planets up here and to the right, but these are the planets, because of that, because we can only detect planets close in, then for Earth-like planets close in, then it turns out all the ones that we can see have this problem. There are lots of planets that don't have this problem, but they're also outside their habitable zone. So as we get more and more data, as we get more planets, as we get better data, we can start to compare where these other planets can be. Ideally, we want them up here. So that's all. So this is a result that we published a couple of years ago. Now, the other thing, let me check the time. We've got 5 minutes or so to do this, and then we can have a couple of questions, I think. And again, this is what the Earth looks like with the Ionis. This is a complicated system. I'm not going to talk you through this. This is energized by high energy radiation from the star, from the sun, ultraviolet radiation and X-ray radiation. And it sets up, it rotates, it's got its own magnetic field. And so you set up a whole range of complicated currents and flows and everything. But what I just want to say so that we know an awful lot about this. We don't know what other planets are doing at all. And so we're having to sort of assume a lot of things here. But the key thing we do know is that when the star is more active, it has more ultraviolet and extreme ultraviolet radiation. And so the planet, and that radiation does not care about the planet's magnetic field. It goes straight into the atmosphere and it ionizes the upper levels of the atmosphere, and it creates a system that looks like this, maybe even more energetic than this one. The solar wind coming off the star, the stellar wind, has its own magnetic field, but the Earth has this large magnetic field. And so it protects us from the particles that come out of the sun, and it protects us from some of the magnetic field. So we can start to model all of that. And now that we've cranked up the activity level of the star, we can see how a planet like the Earth might respond. And so that's what we've been doing. And one of the reasons we want to do this is, can this planet, for instance, you can take a planet, keep it outside the Alfvén surface, but still have it very close to the planet, to the star. If that star is active, the question you want to ask is, does the planet we're interested in have a strong enough magnetic field to protect it from the star? If it does, you can move it in a bit further. You can have the star a little bit more active, all these different things. Now, how are you going to know that? So one of the things that we want to do is calculate and model the interaction. From that interaction, we can work out what the current systems are, and we can work out what the radial emission, the emission that is produced by the planet. Jupiter, for example, we can see in radio emission, a very, very strong source of radio frequency emission. So if we can calculate what the planet's radio emission should be for a given magnetic field and a given interaction with the star, etc., we can then go look at that frequency and look at that, look at that level of sensitivity that we need. And we might be able to measure, or at least infer, the presence of a magnetic field and its strength. And if we know the strength of the magnetic field, we can start to work out how well protected the surface of that planet is. And therefore, assuming it's at the right temperature, it might be magnetically protected from its star. Those would be the planets that you would want to go look for other signs of life. So that's the basic plan. This is for Dr. Amliki. This is our model. So we have the Earth, we have the ionospheric currents up here. We have a grid that allows us to have, this is a blow up of this region. So the solar wind is coming in from the left. Here's your rock in the river, right? This is the Earth's magnetic field. You create a bow shock. You've got what's called a geomagnetic tail, and we can resolve all of these interactions. And this is a close-up of how well we can do that. And so we can work out the response of the planet to this more active star. And this is the kind of thing you get. The key thing that we are adding that other people do not have is most people will model what's called the outer magnetosphere. So this bubble of magnetic field around the Earth is called the magnetosphere. Most people model the interaction with the wind and the upper part of the magnetosphere. What we're able to do is to couple that upper part to the lower magnetosphere using what's called the Rice convection model. This is a model developed at my university. And that lower magnetosphere couples into the ionosphere. So we have this system that connects all the different parts of the atmosphere so that if you energize one part of it, you can feed that all the way through. So the two things that we're going to show you is that this is the wind and magnetic field interacting with the planet Earth, or with this new planet that we're interested in. And in addition, there's electromagnetic radiation that's passing through all of this and ionizing the upper levels. Oops, it looks like I did a little score. Ionizing the upper level of the ionosphere and creating an energized system that can then interact with the magnetic field and so on. So it's a very complex system that is probably more than you want to hear about. So before I show you our results, I just want to point to something for this radio emission. There was this study where if you look at Neptune, Uranus, Earth, Saturn, and then two different emissions from Jupiter, these are the magnetized planets in the solar system. And you compare how much solar wind power is going to the planet and how much radio emission you would expect. It's really nice. They all fall on a very straight line. So it doesn't matter if it's a gas giant like Jupiter or a terrestrial planet like the Earth. The argument here from this study by Zarka, this is magnetic power, this is kinetic power in the wind. The argument here is that since they all fit really well to a straight line, if you crank up the solar wind power, or the stellar wind power, you will crank up the radio emission. And so he calculated that for some of these systems, he calculated that the radio emission would be really, really high and that we'd be able to see it. And so people went looking for it and didn't see it. They went looking at those planets where you expect, if you were to take this straight line and extrapolate it to much higher powers because the planet's close into the star, you expect Proxima Centauri, say, to be up here. You go look for this, it's a huge radio power. You go look for it, it's not there. So there's something wrong with this model. And so that's what we are trying to work on. And what we find is that one of the things you expect is that the atmosphere will become, you can only put so much energy, it becomes saturated. It's a bit like, you know, if you're at the, I guess if you guys are in Jeddah, if you go to the beach, the sand can get super saturated so that the water the sand acts like a liquid because it's completely embedded with water, and then any other water just sits on the top. I'm sure you've seen this when you've been playing at the beach. And so the ionosphere can get saturated and it cannot take any more energy, which means that you should not be able to produce, even though you crank up the power of the wind, you might not expect to see any more power coming out in the form of radio waves. And so some other people did that calculation and they found that was true. And so what we do is we can work out where all these currents are. And when you've got accelerated currents, field-aligned currents, accelerated electrons, that equates to enhanced radio power. And I just want to point you to the bottom curve. So the red line is that previous Zarka result. The blue line is an analytic calculation that says if we allow for that saturation, if we allow for a maximum input to the ionosphere, we would expect the radio emission to drop by a factor of 10. This is just regular solar wind conditions, so don't need to worry about the other plots. So this is good, right? That's why you don't see them. And this was not our result. This came from Nichols and Milan, but this blue curve says the emission would be a factor of 10 smaller than predicted, and that's why we don't see it. Well, then we did our calculations, and what we do is we add in that lower magnetosphere, and our calculations are the green curve. And if you notice, the green curve is above the red curve. So we would expect to see more radio emission than Zarka. So why didn't we see it? And so one of the things we think, well, remember that, and I'm almost done. This is what happens when you do a superstorm. So if you actually look at a storm, a geomagnetic storm from the Sun-Earth system, this is what it looks like. It's a lot crazier. And then we can do the same analysis here. So again, the blue curve analytic, order of magnitude lower than the red curve, which was that Zarka prediction. Our data is in the green, our calculation is in the green. Again, much higher, 2 orders of magnitude higher than the Zarka result. So what's interesting about this was, so Zarka predicts you should see this radio emission. We don't see it. You do the calculation, rather than just extrapolate from the solar system, you do the actual physics. You find that the ionosphere saturates, and so you would expect lower emission. But because we are able to bring in that lower level system, that lower magnetosphere, it turns out that the interaction generates a lot more currents, and all of those currents produce radio emission. So this is good now, because we would expect to see this radio emission from these planets. The reason we don't see it, or why we think we don't see it, is because it's very directional, and that's a kind of complication. So if the radio emission is pointing upwards from where you're looking, you will not see it. And so what we think is that we actually need to find a system in which the angles are all just right for us to be able to see it. So this is really exciting, because instead of having to wait 50 years for the next generation of radio telescopes, we think we might be able to see them with existing telescopes if we get lucky and if we find the right system to look at. So I think that's pretty much it. I won't read this. The key point is, we're finding all these exoplanets. We're really excited about them. There's a large number of them. Many of them look like the Earth, but they're not. We haven't got to the point where we can observe them around a sun. We're seeing them orbit much cooler, smaller stars. But now we're able to do all the physics that we have worked on for decades within the solar physics community and the space physics community, and start to apply these to these stars. And if we can get those observations down, we will be able then to determine which planets have strong magnetic fields, and then work out if they're in the Goldilocks zone and they have strong magnetic fields, those are the planets you want to look for signs of habitability. So with that, I'll summarize what I just said there, and I will thank you, and I hope my translation is correct there. And so, Yassine, thank you for the opportunity. It's always good to talk about this stuff, and it's always good to see you. So thank you.
Thank you, indeed. Thank you very much, David, for this amazing, and usually you are amazing in your lectures since long time ago. But honestly, David, I love the lecture and love the idea that you are making, kind of correlation between the exoplanet sciences and the space weather. And as you know, we have in the university here in King Abdulaziz University and CACS, as well as King Saud University, there are lots of groups who are working on space weather. And I'm sure I had lots of questions into my mobile, and they are very interested for this subject. This is amazing subject. So shukran jazilan. We have a couple of minutes, David, for the questions.
Yes. Okay. Yeah. I've got about 10 minutes or so, just a
10 minutes or 8 minutes. So one of the questions that I had from Dr. Aid Rihali, he said, James Webb Space Telescope, I think it will be launched next year, is it, David?
Well, we'll see. Yeah, but we're hopeful. Yeah, 2020, late 21, early 22, perhaps, if we're lucky.
Do you think?
Inshallah, right?
Inshallah, yes. That's right. Do you think it will help in this kind of studies, or going into more detailed characterization of the planets in terms of magnetic fields?
Well, I'm not sure about the magnetic field, but it's a very good question, because, should I put my slides up to translate again, or?
Yeah, please,
just do it in English.
Yeah,
okay, let me
Amazing.
do this again then.
Great.
Yeah, sorry. Okay, so hopefully the translation will work.
Yeah, I think so.
Is it working? I may have to.
No, it's working. It's okay.
Okay,
I can see.
so it's a very good question.
Yeah.
What I'm excited about, so James Webb Telescope should be able, in some cases, to spectroscopically study the atmospheres of these planets, some of these planets. So it won't be looking at radio emission, it won't be looking at magnetic fields, but it will be looking at the atmospheres. And some of the hope is it will find molecules, compounds, evidence of compounds and so on in that atmosphere that may suggest life. What I'm excited about is because we can couple the star to the magnetic field of the magnetic field of the planet to the ionosphere. There are also models that people do on the Earth for weather and all sorts of things that couple the ionosphere to the atmosphere. So one idea I have is to see with that coupling if in the atmosphere that James Webb Space Telescope will be looking at, can you find signs of magnetic activity caused by the star-planet interaction? So in other words, you might see like again, if you're at the beach and there's a speedboat that you cannot see the speedboat, you're out playing in the water with your child, but now this series of waves come by.
Mm-hmm.
You might not see the speedboat, but because those waves come by, you might infer that somewhere over the horizon was a very fast and large boat that caused those waves. So James Webb Space Telescope will observe some signatures of the atmosphere. And if there's a change in the chemistry caused by the speedboat of the star-planet interaction, we might be able to look at that and learn something about the magnetic field. So it's not direct, but it's one of these things that we're hoping that if we get funding and time that we might be able to explore. So again, James Webb could be really exciting. Other than me, people who are interested on James Webb for planets, they're interested in studying these atmospheres and what they're made of and what that means for conditions on the surface as well. So thank you for that.
Oh, great. Thank you very much, David. I have a question from my friend of mine, Dr. Abdurrahman Malawi. He is from a radio astronomer. He is from our department.
So, he knows more than I do then.
So please, Dr. Abdurrahman. Dr. Aid. Dr. Abdurrahman.
Yes, assalamu alaikum wa rahmatullahi wa barakatuh.
Salam wa rahmatullahi alayhi, Doctor.
Thank you very much, Professor David, for this, wonderful lecture. I actually have two questions. One, what is the frequency range that you are using to measure the radio, emission? And the other question is the Atacama sub-millimeter array is used to, study protoplanets. Can it be used also to detect, exoplanets as well?
Well, again, these are two very good questions, very interesting questions. I am pushing the boundaries of my knowledge here, but so for instance, one of the issues is not just how strong the radio signal is, but what is the frequency. And so some of these we're talking about cyclotron maser instability radiation. If you're obviously, this will be a little bit beyond some of the audience. And so we're looking at, tens of megahertz. Mm-hmm. We're not looking for these just yet. We are trying to predict what the intensity and potentially the frequency will be. But in order to do the frequencies, you really need to know what the particle distributions are and all that sort of thing. So we're looking at relatively low frequencies as akin to what's happening in Jupiter, for example. We did do a study with VLA, and LOFAR might be quite good if you're familiar with those systems. We did this kind of all sky survey with the VLA just to try and see if we could find any aberrant signals in the vicinity of these exoplanets, and we didn't find anything. So that's going to be a challenge. We are working with Caltech to extend the Owens Valley system, and so we'll be the science lead on that. So we might be able to get some targeted observations there. As for ALMA, we have Andrea Isella in our department who has been looking at these protoplanetary systems. So I've been talking to him a little bit. It's a challenge. There are certain modes of ALMA that are not, they're available, but they're oversubscribed, as you know. And there may be some, I've forgotten what mode it can operate in, where there's a chance if you target the right place, you might be able to see something. There's also some excitement about potentially seeing stellar flares and looking at some transient activity. And that's something else that we can start thinking about modeling the planet. So I don't think I'm really answering your question, but I think the frequency range that you're targeting is something I didn't mention, and I think that's crucial. I think that's really important for us to sort of define. There's so many aspects of our model that we have to be careful that we don't predict anything specific, like this planet will produce this much radiation at this frequency, because, you know, again, the star, we need to characterize the star properly, we need to characterize the planet properly. So what we're trying to do is find a range of conditions in which you could at least exclude some planets, right? Don't waste your time looking over here. Much better to look here. You might not find anything, but you have a higher chance here than here. So that's what we're trying to do. So again, hopefully that at least addresses a little bit of your questions.
Thank you very much. Last question. Now you mentioned two conditions, I mean, for the planet to be habitable. One of them is that it must be in the habitable zone, and the other one, it must be outside the Alpine zone. And for those, I mean, dwarf, I mean, stars, because the planet should be very close to the star. What about the star like the sun? Which is it, I mean, possible to find, I mean, the right?
Yes, yes, yeah, and ideally. So here's one other challenge with that. So if you look at the gravitational effect of the Earth around the sun, well, first of all, Jupiter dominates that, so that causes some complication. But an Earth around the sun creates a very small gravitational effect, and so with the current, and even if you imagine some significant advance in the Doppler shift measurement, the radial velocity measurement, the signal to noise for an Earth around the sun is going to be very, very low. Now, in the transit, again, you have to be really well aligned to see from a distance of 30 light years, for example, to see the Earth pass in front of the sun. Now, that's not impossible. If you've got lots and lots of statistics, you might find one or two of those objects. And what was I going to say? So you'd have to be very well aligned, and you would have to have very good photometry, because the amount of light that it blocks will be very, very low. So that's one challenge. The other challenge is, in order to know that it's a planet, you have to see it go around the star many times. So you know that it's not something that the star is doing, but it actually is an object like a planet orbiting that star. Well, if you look at the Earth around the sun, it's a 1-year orbit. So to get many orbits, you would have to observe the same star, 5, 6, 7 years.
Yes.
So now you've got all of this, and you've got this very expensive telescope that everybody wants to use. And you say, nope, I'm going to look at this one thing just in case for 7 years. So there has to be better techniques. Now, just to finish, one quick thing, there's a thing called micro lensing, which is a gravitational lensing. It's basically the fact that a gravitational body will bend light, and therefore it can enhance your signal. People think that microlensing would be able to detect an Earth-like planet at the distance of 1 AU. Now, whether you would categorically state that that's what you saw is another matter, because it's a transient effect. Also, there's a thing called astrometry, where you actually look at how the star itself just moves in space. And if we get, there's a thing called the stellar interferometry mission that probably will never fly, but it's basically doing interferometry from space. And you might be able to see that star move around in space, not measuring its Doppler effect, just watching it move. And they think that you can get to the sensitivity there of detecting an Earth around a sun. So there are people who are very optimistic. But I think what it's going to end up being is having a better understanding of where an interesting system might be, looking at it for a long time and getting lucky. So Yassine, I'm afraid, I really am afraid I'm going to have to run, but I've really enjoyed it. It's been great seeing you again. And maybe we can chat again in the next couple of weeks or so.
Absolutely. I know, David, your reminder has rung 5 minutes ago, I think, and you have very important appointment. We were very pleased and very happy. I had lots of questions. People loved your lecture, and I loved it as well. Thank you indeed. Hope all the best for you. And of course, this is not our last and final talk from you. We will bother you in the near future, maybe a couple of...
Yeah, I'd be more than happy to. We could even set up a question and answer session and forget the talk.
Yes.
Thank you, everyone. Thank you, everyone, for being here. It's always great to reach out. So, Yassine, thank you, man. It's good to give my best to your family.
Thank you. Same to you. Thanks, David. شكرا لكم إخواني وأخواتي زملائي زميلاتي الحضور طلابي. أشكركم جدا على المشاركة، على الأسئلة الرائعة. لم نتمكن. ديفيد عنده موعد حقيقة مهم جدا، ونتمنى لكم التوفيق. والسلام عليكم ورحمة الله وبركاته.
Thank you all. Bye-bye.
Bye-bye.